Welcome back, friends. This is the fourth video of the Environmental Mass Spectrometry series. In this video, we will learn about the basic principle of molecular formula determination. So let's get started. In the third video, our structural elucidation manner was introduced like this. Among these 6 steps, the first and the second steps were already explained in the third video briefly. In this video, the third step, the molecular formula determination step, will be explained in detail. This is the periodic table of the principal elements: hydrogen, helium, lithium, beryllium, etc. You may learn this table in a junior high or senior high school. Please have a close look at oxygen as an example. You may learn the atomic mass of oxygen is 16. But the fact is different. The exact mass of oxygen is 15.9949. All the elements have the exact masses as shown here. To determine molecular formulae of unknown compounds, the exact masses of each element play a key role. In the second video, we learned that time-of-flight mass spectrometer and Orbitrap can measure a mass of an analyte with high resolution. High-resolution mass spec is capable of distinguishing 2 ions of slightly different m/z. Let's see the example of high-resolution mass spectra. For instance, by using a high-resolution mass spectrometer, the ion of m/z 47.0128 can be distinguished from that of 47.0240. Also, 47.0240 can be distinguished from 47.0292. In the cases where a quadruple mass analyzer is used, the masses of all the 3 ions are measured as m/z 47, and we can never distinguish them. The high-resolution mass spec has one more very unique and important feature. Because it is accurate and precise, we can determine the m/z value of unknown ion to 3 or 4 places of decimals. By determining the m/z value of unknown ion to 3 or 4 places of decimals, we can determine molecular formula of unknown compound. For example, if m/z value is 47.0128, it must be CH2O2 plus hydrogen minus 1 electron. The other elemental combinations must give the different m/z value. Similarly, the ion of m/z 47.0240 must be H2, N2O, plus hydrogen minus 1 electron, that of 47.0292 must be C2, H3, F, plus hydrogen minus 1 electron. This is the basic concept of molecular formula determination with mass spec. Let's see the actual mass spectrum. This mass spectrum was recorded by using the Orbitrap mass spectrometer in our lab. The analyte's m/z value was 262.0297. In many cases, we cannot decide on one molecular formula candidate, due to mass error. As for this compound, there were 5 candidates within mass error of 1 part per million. Please note that ppm is the abbreviation for parts per million, namely 10 to the minus 6th power. You may see these 6 exact masses are almost the same value. What now? Please see these adjacent ions. This is the same mass spectrum as shown in the former slide. Please have a look at the most abundant ion. Its m/z value is 262.0297. And the adjacent ion's m/z value is 263.0330. Their difference is 1.0033, which corresponds to the mass difference between carbon-13 and carbon-12, 1.0034. Let's see the ion of m/z 264.0254. The difference between this ion and the most abundant ion is 1.9958. This difference corresponds to the mass difference between sulfur-34 and sulfur-32, 1.9958. That is, these ions clearly indicate that this compound has carbon and sulfur atoms. This is a natural isotopic pattern analysis. But the next question is posed. How many carbon atoms and sulfur atoms in this compound? We can estimate it according to this equation, where Im, the blue-colored arrow, is the relative peak intensity of the most abundant peak, namely it is 100. Im plus N, the red-colored arrows, are the relative peak intensities of isotopolog ions. For example, in the case of carbon content analysis, Im plus 1, illustrated in the red arrow, is about 0.09. A is the number of carbon atoms. Im and Im plus N will be shown in the next slide. As you know, many atoms have stable isotopes. Their relative isotopic abundance ratios in nature are almost stable. For instance, the natural abundance ratio of carbon-13 against carbon-12 is 1.082%. This is an example of Im plus N in the former slide. And Im is always 100. Please note that, isotopic abundances of each element are expressed, with the abundance of the most abundant isotope, normalized to 100% in this manner, because the mass spectrum works with relative percentage isotope abundances. Let's see the same spectrum again. Im plus N, Im plus N and Im, all the parameters to calculate A were obtained. Let's see the detailed calculation. By using the observed relative intensities of the isotopolog ions, as well as their natural abundances, the number of carbon and sulfur atoms are calculated to be about 9 and 1, so the molecular formula of this unknown compound is decided to be C9H13O4NPS. As shown here, we can decide the molecular formula of the unknown compounds. This is the way to determine molecular formulae of unknown compounds. That's all. Thank you for watching.